Drilling is another. It involves quite a different kind of cutting tool, one that produces holes. And from drilling to milling. This particular milling cutter is designed to operate at high speeds and feeds. It's producing a flat surface. Here we're turning brass. Engineers must be able to cut all sorts of different materials and on almost any scale. This is one of the largest lathes in the country. Industrial machines are often designed to take more than one cut at a time. Cutting tools are usually made of high-speed steel, but here the cutting edges are made from a much harder material, tungsten carbide. But whatever the tool is made of, or the cutting process involved, one thing must always be there: movement. On a shaper, the tool moves with respect to the work, cutting or generating a flat surface. The work is clamped to the machine and remains stationary during the forward or cutting stroke. During each return stroke, the work is moved sideways, ready for the next cut. Vertical drilling is a process where only the cutting tool moves. It rotates, generating a hole in the component. The component can't move, it's clamped in a vise fixed to the machine table. But there's more to it than that. The rotating drill must be fed or traversed into the work in order to cut. Milling is another process where the tool rotates, but instead of the tool being fed into the work is fed in towards the revolving cutter. In this way, a flat surface is generated. In the case of the lathe, it's the work that rotates with respect to the tool. The cutting tool can be fed into the work along the machine bed. Feeding in this direction, a cylindrical surface is generated. Using a different cutting tool, we can also feed into the work across the machine bed. In this way, a flat surface is generated. Let's take a closer look at some of the cutting tools used in engineering. This is a cold saw. It's used to cut through huge slabs of steel. The blade is made up of a number of cutting edges or teeth, each similar in shape. They have what's usually described as a wedge shape. How does this compare with the shape of the cutting edges on other tools? The teeth of a hacksaw blade, for example. Like the cold saw, each tooth here has a similar shape, a wedge shape. And what about the cutting tool we're using on this milling machine? Again, several cutting edges, but the shape's the same. This is a lathe tool, a parting off tool. This time we have only one cutting edge. Again though, a wedge. A twist drill looks quite different to most other cutting tools, but even here the cutting edge has a similar shape. Now, why do all these cutting edges have the same basic shape? To find out, we went to the Institute of Technology at Cranfield. Here we set up a special experiment on a planer. First we tried cutting a piece of mild steel this way, with a square-ended cutting tool. The face of the tool is at right angles to the work. And the bottom touches the work all along its length. On a planer, the work moves to and fro. To take a cut, the tool has to be lowered. Did you see what happened? Let's take a much closer look at that in slow motion. Here you can see how the chip forms. For an efficient cut, the chip should flow naturally over the face of the tool. It doesn't flow naturally here. Instead, it's being compressed and it's tending to break up. Not only that, the bottom of the tool is rubbing on the cut surface. This is causing the tool to ride up over the work until it stops cutting altogether. The surface finish has a very rough look about it. And what about the cutting tool? Let's see if it's damaged in any way. What you see here is the bottom of the tool. Here's the cutting edge. Near the back we find traces of material from the work, material that's welded onto the tool as a result of the rubbing action. Now we can prevent this from happening by changing the shape of the tool. To do this, we're using a machine called a cutter grinder. All we're doing here is grinding away the part of the tool which was rubbing on the work. In other words, we're making the bottom of the tool slope away from the work. Now only the cutting edge touches the work. The angle formed between the tool and the work provides clearance. We call this the clearance angle. Let's see how this affects the cutting action. The tool cuts for the full length of the work. But have we changed the way the chip forms? Here's the cutting action in slow motion. The chip still doesn't flow naturally over the face of the tool. It's still being compressed and deformed. Now we can improve on the way the chip forms by changing the path that it takes over the tool face. This means making another modification to the shape of the tool. Again, we'll use the cutter grinder, but this time with a different wheel. Here we're changing the angle of the tool face. The cutting edge now has a familiar shape. Here's the angle between the bottom of the tool and the work, the clearance angle, and here's the angle we've just formed. It's called the rake angle. And let's try taking another cut. This time the chip seems to form in a much better way. But it's worth a closer look, again in slow motion. Can you see the difference? The chip is beginning to flow more naturally. And look at the way it shears from the parent material. It seems to come away along a line that's almost at 90 degrees to the tool face. Let's look at the shearing action in this model. As the tool cuts, the chip shears along this line here, but that's from the front. In this model, you can see that a chip has width, so it must also shear along a similar line for the whole of its width. If we take the tool and the chip away, this line becomes a plane. It's called the shear plane. In fact, we usually refer to the shear plane by this line here. The length of it being called the shear plane length. Here's the cutting action in slow motion again. Now, if you look carefully, you'll notice that the position of the shear plane is changing. And look at the material building up at the cutting edge. This disturbs the way the chip flows and will affect the surface finish. Remember, this surface is the result of giving the tool a 5-degree rake angle. What happens if we increase the rake angle to 15 degrees? We seem to be getting an even better chip formation. Here's the cutting action in slow motion. This time there's a much more natural flow of material over the tool face. This is a good chip, and can you see the shear plane? Again, it's almost at right angles to the face of the tool. Let's compare this shear plane with the one produced by the tool having a smaller rake angle. In this diagram, the rake angle is 15 degrees. Watch the shear plane as the angle decreases. Did you see what happened? The length of the plane, that's this distance, increased. So by changing the rake angle, we changed the length of the shear plane. The larger the angle, the shorter the plane. The smaller the angle, the longer the plane. A lathe is just one of several machines used for cutting materials. While cutting, the machine uses power, in this case, electrical power. On this lathe, a meter shows just how much power is being used. It's measured in kilowatts. Now, one factor that can affect the power is the shape or geometry of the tool. This is a knife edge tool. It has a clearance angle of about 6 degrees and a rake angle of about 15 degrees. Let's find out what happens if the geometry of the tool is changed. Here we have 4 knife edge tools, each with a different rake angle. Their clearance angles are all the same. For this experiment, we'll use this specially prepared piece of mild steel. We've taken a core from the middle to make it easier to film. First, we'll try the tool with a 10-degree rake angle. The tool must be carefully positioned and properly restrained. Before cutting begins, the lathe will use some power for turning the work round, and even more power is used when cutting starts. The total 2.6 kilowatts. Next we'll try a rake angle of 20 degrees. Same speed, same feed. And the total power used, 2.3 kilowatts. Now a rake angle of 30 degrees. Same speed, and again same feed. And even less power is needed. Finally, a rake angle of 40 degrees. This time, the power used is, well, what do you think it is? Less still, 2 kilowatts exactly. Let's put these results on a chart. For 10 degrees rake, the total power used was 2.6 kilowatts. For 20 degrees, 2.3 kilowatts. For 30 degrees, 2.1 kilowatts, and for 40, 2. But for each test, the lathe was using some power before the cut began. To get the power used in cutting the material, we must subtract this from the total power. So, the larger the rake angle, the less power is used. Now this must be related in some way to the shape and cutting action of these tools. As with most cutting tools, the material is sheared along a plane at 90 degrees to the face of the tool, the shear plane. The length of this plane, that's this distance, is determined by the rake angle of the tool. Here the rake angle is 20 degrees. The larger the rake angle, the shorter the plane. The smaller the rake angle, the longer the plane. Let's compare the length of this plane with the power used. Can you see what's happening? The power seems to depend on the shear plane length. The shorter it is, the less power is used. By giving a cutting tool a really large rake angle, there'll be a very short shear plane and little power will be used. But just how serviceable is a tool like this? After only a few moments' use, the cutting edge is damaged. Damage like this is expensive, so is excessive power consumption. So this business of choosing the right angle is very important. From these results, a tool with a rake angle of between 10 degrees and 20 degrees, say 15, would be the most suitable. But that's for one material. Free cutting mild steel. There are other materials such as brass, aluminium and nylon. Would, say, 15 degrees be the right rake angle for cutting any of those materials?